force times displacement is actually equal to work. So even if you carry an elephant and you simply stand under the sun, it is not considered to be a work. So mg, mass, is being pulled down by gravity. Let's say this is gravitational force. So work done is actually equal to Newton meter. Or again, you can just say that this Newton meter is also equal to joules. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a very brand new chapter, that is work, energy and power. What are these three concepts? How are they related? And is there any relation between them? We'll all see very soon. So, introduction to work. So, what exactly is work? What exactly is work? Is it waking up in the morning, brushing and going to your jobs that you do? Maybe you're an engineer, maybe you want to become a doctor, maybe you want to become a painter, maybe you want to become an analyst. I don't know. Maybe you want to become a lecturer. I still don't know. So is that work? In common man's or in layman's terms, we can say that, okay, that is work. We get up, we go to a work, and that is our employment. That is generally termed as work. But in physics, we cannot say that is work. If a person is getting up early in the morning, hard working in the hot sun, I won't say that is work unless specific criteria are met, that is explained by physics. So, what actually physics says is that for anyone to do any work, it means that they have to apply a force and a specific displacement has to be produced. Then only it will be termed as work. So, we can say that if a person who is hardworking, very hardworking, he gets up early in the morning, he goes to a bus stand or a railway station, he's a porter, he's working very hard and supporting his family. And like that poor man, he's working his life off and he's supporting his family and he's daily standing in the hot sun carrying weight like this. So this is a box which is containing around 50 kgs. He's standing in the hot sun carrying this box just like this. Now he's working. His work is just carrying that box, standing there till evening and he'll get paid a good amount. But for a physicist, this work is zero. That is, he's not doing any work. It's very sad, but from a physics standpoint of view, he's not doing any work. Because what physics explains is that if there is any object, or if there is any object like this, if a force is applied onto it, retake. So if a force is applied onto it and this particular object displaces, that is, it changes its position, then we can say that he is doing a work. So if any man who is pushing this box and it is moving, then we can say that there is work done here because the definition of work is equal to force times displacement. So force times displacement is actually equal to work. So even if you carry an elephant and you simply stand under the sun, it is not considered to be a work unless there is a force being applied and displacement being produced. So that is known as work in terms of physics. So again, we can generally say that if there is any quantity here and we are applying a force and it produces a displacement or it displaces through a distance of, let's say, s, then we can say that that particular product of these two will be known as work done. But sir, is there any other quantities or anything hidden for this particular thing? Yes, there is, because it is not just the force applied and displacement produced. Of course, that is generally known as work, but there can be specific situations or general examples where different possible configurations or different setups can be done. That is, I can not only apply force like this, I can apply force like this, I can apply force like this at a particular angle. Now, friction is also opposing this particular motion, which means frictional force is acting in this particular direction. Let's say frictional force is acting in this particular direction. Gravitational force is acting in this particular direction. Gravity is pulling down on it, right? So mg, mass, is being pulled down by gravity. Let's say this is gravitational force. It is acting downwards. So many things, many forces are acting on this particular object. But can I say that if this load is standing like this and gravity is pulling down on it, is gravity doing work? Absolutely not. He's pulling down like this, but the displacement is happening in that particular direction. So how can I define, how can I say that, okay, gravity is not doing any work, or this man is doing the actual work, or this frictional force is doing the work? How can I actually say that? So again, for this all things, that is, if I am pushing the box and gravity is pulling down on it, they're asking, okay, who's doing the actual work? So to avoid all these confusions, again, we have to consider what is the angle at which this particular force is being applied, or the angle between the force applied and the displacement produced will actually yield you the net work done. So we can actually say that work done, which is indicated by W, is equal to just F times S. That is the general definition, F times S. Both are vector quantities. This is not a cross product, this is just multiplying. So F times S, or we can say that W can also be written as F dot S. So remember, work is actually a scalar quantity. Why? Because it is A dot B. That is AB cos theta. Here it is F dot S. So what is F dot S means? It is just to include the angle between them, which is equal to Fs cos theta, which is equal to W. This is one more important equation. So we can see many things from this particular equation. The first thing is that it is a scalar quantity because it is A dot B. So for scalar quantities, it is actually dot product. So for vector quantities, it will be actually cross products. So since work is a product of dot product, we can say that work is a scalar quantity. And then the next thing is that it is the product of force and displacement and the angle between them, cos of the angle between them. So that is one more information. And finally, we can also predict the SI unit. So we can actually say the SI unit of work, which is given by this particular equation. Force is nothing but Newton and displacement is nothing but meter. Very good. So you'll get the SI unit as Newton meter. So work done is actually equal to Newton meter, or again you can just say that this Newton meter is also equal to joules. So we can also say that work done is actually equal to joules. So another SI unit is joules. Joules is a scientist and he worked extensively in the energy projects. So that is why with respect to him or paying tribute to him, we named certain units as joule. Generally it is for energy, but here work will have the same dimension. So we can say that it will be equal to joules also. So again, we figured out the SI unit, we figured out the general equation. Now one more thing remains. What if I push this box and the box only moved a small distance? That is, if I push this box and the box only moved a small distance, then the displacement is very small, indicated by delta S. So we can have two more equations, that is W is equal to F delta S. That is, or I can say that del W, that is the small work. Delta signifies change or small quantities. So the change in work or the small work that is I am doing is actually equal to force times the small displacement that is produced. Now that is when we actually use the summation symbol, but we can generally say that dW is equal to FdS. That is, dW signifies the small amount of work done and ds is the small displacement that is produced. When we are dealing with differentials and integrals, we generally use d and dt. d by dt, d by dx, all that. So we use differentiation or calculus, and here it is just the summation symbol, that is generally we use delta and sigma and all that. But now we are going to deal with integrals and differentiations, so we have to use d. So small work is equal to the small displacement that is produced when a force is acting on any object. Now, is everything done? You think it will be done, but there's one more problem. Since I have applied cos theta to this particular equation, there is a problem. Cos can be 0, cos can be plus 1, cos can be negative 1. So we actually get a positive work, we get a 0 work and a negative work. So we get positive, negative and 0 output, which means that depending on the angle, it can be positive, negative or 0. Depending on the displacement, it can be positive, negative or 0. So how do we get that? Again, the equation for work done, W is equal to F dot ds, right? F ds, that is F ds cos theta. So when a force is applied and a small displacement is produced, we can say that work is done, and we can write that particular formula as F ds cos theta. What is that small work done? Okay, so let's consider a case. There is a box like this. I'm pushing on the box and the box is moving, let's say about a small distance. A box will be too small, right? Every time I'm taking box, I'll take a shelf or a cupboard. Let's say this is the cupboard in my room. I mean, it's generally a cupboard. So I'm pushing it. Since it's very heavy, I'm pushing it and it only moved a little bit. So that is why the small displacement is there. So again, I can write this. Now I'm going to measure what is the angle between the force that is being applied and the displacement that is being produced. So since the force applied and displacement both are parallel to each other, the angle between them will be 0 degrees. So I can say this is equal to F ds cos 0. What is cos 0 degrees? It is nothing but 1. So we'll get the output as F ds. So W is equal to F ds, which means if a force is applied and displacement is produced in the same direction of which the force is applied, then that is known as positive work, because we have a positive value. So when force applied and displacement produced is in the same direction, that is force applied and displacement produced both are in the same direction, like pushing an object, pushing a box, pushing your friend and the friend being moving forward, then we can say that force applied and displacement produced both in the same direction, then that is known as positive work. So that is known as positive work. When the force applied and the displacement produced is in the same direction, that is known as positive work. Then is there a negative work? Yes, of course there is a negative work. That is, when you apply a force in one direction and the displacement produced is in the opposite direction, then that is known as negative work. In mathematical terms, we can say that W is equal to F ds cos. When is cos negative? Cos is only negative when the angle is 180 degrees. Right? For 0, it is 0. For 180, it is negative 1. So we can see that it is F ds into minus 1, or simply W is equal to minus F ds. Sir, this is absurd. How can I push something and the object will go in the opposite way? It is basically saying that if I flick it or if I apply a force, this should actually come in the opposite direction. That is ridiculous. That is not logic. Don't worry. It is absolutely making sense, because you have to only consider the right situation. For example, if there is a well like this, let's say this is a well, and I have to take water out of it. I have two options. I can stand here, right? I can stand here and I can use a bucket and a rope, tie the bucket to the rope, I can dip it in, pull it out. Now that is slightly difficult, so I use a pulley system. That is what generally you do if you have a well. So there will be a pulley through which a rope will be hanged, which means I am pulling the rope downwards and the bucket of water is coming upwards. So again, I am pulling the rope downwards, the bucket of water is coming upwards. In physical terms or in terms of physics, we can say that I am applying the force in the downward direction, but displacement S is happening in the opposite direction, which means the two angles are acting at 180 degrees, or two vectors are acting at an angle of 180 degrees. They are lying anti-parallel to each other. I'm applying the force downwards, the displacement is happening upwards. So simply I can say that since the angle between them is 180 degrees, then work will be negative work, and that is known as negative work. A well-known example is drawing water from the well using a pulley system. Pulling on the rope downwards and up comes the water. The water is coming up, I am pushing down. So force is down, displacement is up. So that is how you apply the logic. So you can actually say that there is negative work, there is positive work. Now when there is zero work, yes, absolutely. When the angle between them is 90 degrees, it is zero work. So for example, I can see that again, f dot ds, f ds cos theta, when cos theta or theta, when theta is equal to 90 degrees, work done W will be equal to 0, because cos 90 is nothing but 0 degrees. That is one thing. And there is another possibility, even though you are applying a force, there might be no work produced because there is no displacement. Now, where is that particular situation where I apply a force and no displacement is produced? That particular example is if I push on this particular wall. I'm not going to push, this might fall down. So if I push on the wall as hard as I can, there is no use. The wall is not going to move unless I'm Superman. So, and I'm not Superman. So if I push on this particular wall, not this smart screen, on the wall, if I push on it with all my strength, the wall is not going to move, which means there is no displacement being produced. There is no displacement being produced, S is 0. Then according to the equation, W is equal to F times S, then we can say that since S is equal to 0, work is equal to 0. So I can say that pushing a wall is actually idiotic, but in terms of physics, it's an experiment, and that yielded the result that pushing a wall is actually 0 work. So pushing a wall is actually considered as 0 work, because even though you're applying a force at a particular angle, the wall is not moving, hence it is 0 work. One more example in terms of angle which you can consider is that if I am keeping the box on top of a table, like this, then obviously the box is having a mass m and gravity is pulling down on it with g, acceleration due to gravity, and the net force that is experienced by this box is in the downward direction, which is mg. So we can say that F is equal to mg. So F is equal to mg, one force is acting downwards. Now I am going to push this particular box in this particular direction, the horizontal direction, which means I am applying a force. So if I am applying a force, this object is going to move in this particular direction. Then I can say that with respect to my perspective, I am applying the force, the object is moving in that particular direction, which means displacement is being produced, that is S displacement is being produced. I am applying the force in that particular direction, box is moving in that particular direction. So hence I am doing positive work. But the frictional forces on this particular table, friction is an opposing force. The frictional forces are trying to go in this particular direction. So frictional force is acting in the opposite direction to the displacement. So in view of the frictional forces, if I become the frictional force, I am applying the frictional force in this particular direction, but the displacement is going in that particular direction. So right now the work done by the frictional force is acting negatively. So that is negative work done. And finally, if I am taking gravitational force, gravity is pulling down on it so hard, but nothing is happening because the angle between the displacement, that is displacement is in this particular direction. So displacement and this particular gravitational force, if I draw a line like this and displacement like this, they are acting at an angle of 90 degrees, which means he's doing zero work. That here they are doing zero work. Gravity is actually doing zero work because the angle between gravity, that is the force acting downwards because of gravity, and the displacement which is being produced is at 90-degree angles. Hence, no work is done by gravity. Even though gravity is constantly pulling us down, in this particular case, gravity is doing no work. So that is how work is actually defined. If you want more relatable examples, there is more relatable examples. That is, if I consider a slanting surface like this, and if I place a box like this, and if I apply a force, if let's say it is automatically sliding down, then frictional force will be acting in one particular direction here, opposing this particular force or change in motion, and gravity will be acting downwards. Normal reaction will be acting perpendicular to this particular surface. Then what will happen? The displacement produced is in this particular direction, right? Displacement produced is in this particular direction. So displacement is happening and there is a force being applied. So again, if I measure the angle between them, I can clearly say that the angle between Fs, that is force and normal reaction. Always remember, normal reaction is equal to gravitational force. This mg is equal to n. So I can clearly say that since the angle between Fs and n is always 90 degrees, here work done is again 0 because these two are acting at 90 degrees with each other. Normal reaction and this particular force, or again the displacement, is acting at 90 degrees with each other, which means force and displacement are acting at 90 degrees with each other. It is 0. N and S. This will be equal to this and this is at 90 degrees, hence it is 0. That is very simple. Again, if you are taking one more example, that is centripetal acceleration. If you are taking centripetal acceleration, we know that force is directed inwards. This is centripetal force. And if you are taking velocity vector v, again the angle between them is again 90 degrees. Hence the work done by the car is equal to 0 at that particular point in time, because it is not that the car is not being driven, it is not that the engine is doing anything. It is because the angle between these two vectors are 90 degrees. Whenever the angle is 90 degrees, automatically the work done will be equal to 0. Now again, these are all physical examples. What about mathematical examples? So there can be a possibility where they can ask you a question in terms of mathematical reasoning, or simply they can say that, okay, I have a force which is indicated or represented using the formula, I plus 5j plus 7k. So this is again representing a vector. So force is represented like this, and they are saying that, okay, then displacement vector is actually represented and displacement of this particular particle, that is a force was applied on a particle and it is given by I plus 5j plus 7k, and displacement was produced by 6i minus 2j plus 3k. Then they are asking what is the net work done on this particular body, what is the work done by the forces. Then you can actually say that, Okay, I have a mathematical formula, that is W is equal to F dot S. Then you can actually use that particular formula and find out what is the net work done. For example, I have F, I have S, so I know the equation, that is W is equal to F dot S. So you can actually take the dot product of these two vectors. So A dot B, I into I, J into J, K into K. You can just directly multiply it. Then you will have the output as 6 into 1 plus 5 into minus 2, that is minus 10, plus 7 into 3, that is 21, and you will get the net output as 27 minus 10 as 17 Newton meters. 17 Newton meters, or you can also write it as 17 joules. So these are the two ways you can actually find out what is the work being done. You can use the physical aspects where you can apply logic, or you can just use the mathematical aspect that also will give you the right result. So since we are applying the mathematical logic, I'll tell you what the area under the FS graph also gives. That is, if I can represent force on one axis, let's say this is the y-axis, and I'm representing force in this particular axis, and if I am representing displacement S in the x-axis. So if I represent displacement and force in respective axes, then I can say that if this is the graph, I applied a force and it was not even, it was uneven. That is, I kept trying, I took a rest and I tried again and I applied more force. So that is why this curve is there. So when I applied a particular force and displacement was produced, then I can say that this is the nature of the graph, and I'm asking you what is the work done. So again, it's very simple. You know the formula, you have to apply the logic. That's it. So the equation for work done, W is equal to F dot S, or F times S. Then we can actually say that the area under this graph, the area under this particular graph, the area under this particular graph will be equal to work done. So what is area? Area is equal to length into breadth, or simply here it is y into x. Here y is nothing but f, x is nothing but s. So it is f times s. F times s is nothing but work done. So area under, that is area under the FS graph will give you work done. Right? The area under the force displacement graph will give you the net work that is being done. If you remember, if this was time, then it will be Ft. What is F delta T? If I take a small area, what is F delta T? F delta T is nothing but impulse. We learned it in the fourth chapter, that is the previous chapter. So again, if there are bends like this, we can only do one thing. Small areas we'll add them together. We'll take the small areas, add them together. Again, we'll get what is the work done. So again, remember, the area under this particular graph, FS graph, will give you what is the net work done. So I hope you have understood what work means in physical terms, what positive work is, what negative work is, what zero work is, or also known as null work. What is that, and how an angle influences work done, how physically it differs, how a negative work is obtained, and how, if there is a mathematical formula or a vector representation, how you can take work done. I hope that is all clear. I'll meet you all in the next class dealing with energy. So until then, thank you.